Okay, so off we go. Here's where we left off from last time. So you recall we were doing integrals in polar coordinates. And so we're going to do one more example of that by considering this integral right here, which you'll notice is single variable, and thus bringing up the question of why would we be interested in such a thing in this context. So here's the answer. It turns out there's an extremely important integral. It's very hard to compute, and believe it or not, polar coordinates is going to be the trick. Now, why is this an important integral? Well, this is what y'all may have seen in some other context. It's called the normal distribution, sometimes called a Gaussian distribution. Extremely important in statistics. And exactly why is a wonderful topic for another occasion, not now. And of course, you compute probabilities by computing integrals. So if you think about it, this integral here relates to probability of arguably the most important distribution that is studied. And so kind of a big deal. So now how are we going to compute this thing? The weird trick is to compute the square of it. I'm going to multiply it by itself of all weird things. And when I do that, I can do the following little fast ones. I'm going to look at this, make the observation that that's just some number. Right, it's easy to kind of get lost in all of the notation and feel like surely that's a function or something. But no, this is a number because we're evaluating from negative infinity to infinity. Right, so this is just some value, and numbers can pop right inside of an integral like that. Okay, now the result is an iterated integral. Okay, now let's recall. When you're doing an iterated integral, the integral on the inside, right, as far as it's concerned, the outside variable is a constant, and therefore, with y being constant, then e to the negative y squared is a constant. So it will pop inside of that integral, like so. All right, so this is kind of a weird little combination of tricks, and yet what we've got now is a product of two integrals has turned itself into an iterated integral, which is not hard to turn into then this double integral. Now let's talk about that for just a moment here. Why is this a double integral? These values just have x and y ranging over the entire xy plane, aka R2. Right? And of course, this integrand here from basic algebra, you can rewrite like that. Okay, so now as I like to joke here, we have now successfully turned a question that is a hard question now into instead seemingly an even harder question. Right? And you'd be surprised how often it happens in math that the way to solve a hard problem is to first turn it into an even harder problem. And then different context, different tools become available, and mysteriously you can solve the harder problem more easily than the original problem. So in this case, the new context is that we've got this written as a double integral. And if you think about how you do this double integral in polar coordinates, well, area in the xy plane is now r d theta in polar coordinates. And e to the negative x squared plus y squared just becomes e to the negative r squared. And in polar coordinates, we get the entire plane by this range of values of r and theta. Right? Theta goes all the way around. R goes all the way out. Right? And with that noted, here's our new integral. Now, a complaint could be made. Look, I still have that e to the negative whatever squared. That's still going to be a hard integral to compute, isn't it? But in fact, no. That's not my integrand. That's my integrand. And this is susceptible to a really easy u substitution. Just let u equals negative r squared, and then you can see that's going to be kind of a du right there, except for the constant or whatever. And this is actually a really easy integral. Perfectly doable, yeah.
I was just going to say, since we multiplied itself in the beginning, don't we have to like take the square root?
Totally. Yeah. No, that's exactly right, and that's the very last step here, and it is easy to forget that. But yeah, totally. We just computed j squared to be pi, and so j is square root of pi. Yeah, absolutely. Yeah. Cool. So anyway, it's a weird little trick, and again, it's a classical calculation first done hundreds of years ago, but a brilliant little move to take an otherwise intractable integral and turn it into not that bad of a calculation. So, gotta love it. Okay, moving along. Cylindrical coordinates. Shockingly similar to polar coordinates. We can use the conversion formulas as a change in variables function. We already talked about that. We've computed the stretching factor previously. I know how pullbacks work, right? I can talk about a domain in XYZ space and pulling back into R theta Z space. And sure, I could take my original domain, reinterpret as a pullback domain, and then slice it up with actual theta slices. For example, like this, that's a theta slice perpendicular to the theta axis. But notice, just like with polar coordinates, if I can just understand what those theta slices look like over here in XYZ space, I don't need to pull back the domain to do the theta slicing. I can see how the theta slicing goes down here, where I already have my original domain that was given to me. Okay, so just like in polar coordinates, the only difference is in what those slices look like, and of course the fact that it's three-dimensional. So we're going to do a couple of examples of this. I'm going to start with the tips and tricks. Good news, these are the only 2 of your 6 options that you ever need to bother with. Don't even think about the other 4 options of how you can order those differentials. You will not need them. It's just very rare. It's and extremely unnatural for such cases to arise. So now how are you going to memorize what these 2 are? The big trick is to observe that R and theta are always together, and R and theta are always in the usual order, dr d theta. And that leaves then only sort of the one question of whether dz is going to be on the outside or the inside. So real easy to remember. And these are the only options you ever need to play with. Per the speech I gave last time about always put the R in there. When you write down your differentials, don't ever forget to put the stretching factor in at the same time. It's surprisingly easy to forget. So many students forget, right? Because they get distracted with the geometry of the bounds and conversion formulas, etc. Please, as you're writing down your differentials, write this down all at once. Stretching factor and differentials together. And if you follow that rule, then you won't forget. Okay, so let's see some examples, starting with this one. Here we go. We have this upper half ball, like so. That's going to be our domain for a triple integral. Why are we computing a triple integral in this domain? Whatever, doesn't. Maybe we're computing the amount of mass, or who cares? Okay, well, here we go, slicing it up. It seems that we're starting with theta on the outside. Remember, we have 2 reasonable options. I'm going to start with theta on the outside here. That reminds me, I don't know if my phone's off. Yeah, okay, cool. So with theta on the outside, for no particular reason, here's what a theta slice looks like. This is the resulting slice of my solid. And now we ask, what are the relevant values of theta, right? For which values of theta do I get actual, chunk of solid? And I think it's a pretty easy pitch that theta goes all the way around, right? So whenever it goes all the way around, 0 to 2 pi are the bounds. Is everybody happy with that? Okay. Right, okay. So moving on to the next step then with theta fixed. In other words, if my attention focused only on this theta slice, Next question. What's the range of values of r? Okay, now, we've got to think geometrically here. First, what is an r slice? An r slice represents a constant value of r. For example, let's think about this value of r here. This is the collection of all points that are, whatever about yay so far, that are this fixed distance away from the z-axis. So all of the points on this purple cylinder are the same distance from the z-axis. So this is a r slice. Now, how does geometric appeal here? How does our green slice intersect with our r slice? Oh, it intersects in that shape right there. Kind of a little line segment. Right? So, as usual, we have to think about first and last. The first such slice, I'm going to say, is about like this. What can I say about that? Well, it's on the z-axis. That's where r is just straight up 0. So I start with r equals 0. My last slice, now again, you imagine these r slices, proceeding along, and the further you go to the outside, the shorter they get. The very last one then being just this point right there. Now I need to think through what is the value of r at that point, and you can think about what surfaces that's on and write down some algebra and do some resulting calculations and get an answer, and that's fine, and it'll get you the right answer. But I like it when there's a quick little workaround, and notice that the value of r, namely the distance from the z-axis, happens to also be a radius of this sphere, which I know the radius of, namely a, right? And so very conveniently that point, giving me the upper bound for r, is a. Does everybody buy it? Alrighty, so handy. Okay, now, with both r and theta fixed, in other words, looking at this r slice of our theta slice. It's our usual sort of structure for how we go through these iterated integrals. Now looking for z. What are the starting and ending values for z? All right, well, we're going to start at that point. What can I say about that point? Well, again, sometimes it's a freebie. That point clearly in the xy plane. Thank you, picture. Xy plane defined by z equals 0. So my lower bound for z is 0. Right? My last value of z is at that point. Now here we're going to have to do a little actual work. That upper bound point is on this sphere. Now again, the picture is what tells us that, right? So the picture is really important. Make sure it always has a good picture. What's the equation for that sphere? Well, I've got to write the equation for that sphere in cylindrical coordinates. Flashback to chapter 1 where we talked about such things. And there it is. Now, don't lose track of what we're doing. The reason I'm interested in this equation is because that describes my upper bound for z, which means in that equation I need to solve for z. And when in that equation you solve for z, you get that expression, which is our upper bound for z. And there we go. There we have our iterated integral, cylindrical coordinates. Is everybody happy? Okay. Now, I didn't say so at the time, but let me point out, you'll notice that, again, it was pretty easy to kind of get distracted. We were thinking about the order of the differentials and the corresponding picture and all the bounds and the slices, and oh my gosh, and did you notice it would have been pretty easy to lose track of that R, wouldn't it? So anyway, make sure you don't forget. And again, I think the best way to make sure you don't forget is you don't ever write this down by itself. Don't ever write down dz dr d theta by itself. Why would you? dz dr d theta by itself, it's not a thing. It serves no purpose. Right? You will never need it without also needing the r. So always write down r dz dr d theta instead. Okay. All right, next example, we're going to do the exact same domain, just now this time we're going to put dz on the outside instead of the inside. And okay, so our usual slicing process, here's what a z slice looks like. Constant value of z, horizontal plane. Here's what the resulting slice is. It's a disk. You think about first and last. The first one is going to be down here, where z is obviously 0. Right? The last one is going to be up here at the North Pole, as it were, which again, that being a radius of the sphere, gives me z equals a. Is everybody happy? All right. So there's our z bounds. Now, as usual, we're going to fix our attention to just that one value of z. And on that z slice, now let's think about theta slices. Okay, what's a theta slice? A theta slice is a half plane like so, hinged on the z-axis like we've talked about before. So I have to, again, use my geometric intuition here. How does that blue half plane intersect with that green disk? And you just have to see the geometry, right? And the intersection is going to be this little line segment, like so. And then, you know, our usual question, what ranges of values of theta actually give us a cross-section there? And again, I think a pretty easy pitch. It goes all the way around, right? So 0 to 2 pi for our theta bounds. Everybody comfortable with that? Okay, and then, as we usually do, now I'm going to look at just my theta slice of my z slice, as previously discussed. Now on that, we need to look for our r bounds. And r starts at that point where obviously r is 0, thus giving us our lower bound. R ends at, well, okay, so that point, that red point, let's see, let me get rid of that thing. That red point, which again, thank you, picture, is, I can see on the sphere. And so again, I find myself looking at the same equation for the sphere. Now this is going to play out a little bit differently. Up here, we were looking at the equation of the sphere because we were interested in finding the upper bound for z, and so in this equation we solve for z. Right? But no longer. Now, same equation, but now I'm trying to find the bounds for r. And so now, even though it's the same equation, I need to now solve for r. And that becomes my upper bound for r. Everybody good? All right. Cool. Spherical coordinates. Not that different. Geometrically different. Yeah, right? But structurally, same idea, right? The conversion formulas are a change of variables function for which we already know the stretching factor. We know how pullbacks work, and yes, I could take my domain and do the pullback, which is geometrically really challenging, and then slice it up in the usual way. Or, much easier, I can just stick with whatever my original solid was and just understand what spherical slices look like in XYZ space. And it's just a much easier approach. Right, so we got to think these through, and a theta slice, you know, representing a constant value of theta, as usual, looks like this. Again, I like to think of this as a, in my mind, I imagine a little door where the hinges are on the z-axis, right? Kind of rotates around. Right? So I like to call this a half plane hinged on the z-axis. Let's see here. Okay, looking at phi slices, right? Perpendicular to the phi axis. If I look at what do those slices look like. Okay, constant value of phi in XYZ world. A constant value of phi looks like this. It's a cone. because, again, keep in mind, phi measures angle off of the z-axis. And every point on this cone has the same angle off of the z-axis. Is that cool? Is everybody happy with that? Okay. So that's a little weird. And then even weirder, what is a rho slice? Okay, well, if I want to look at a constant value of rho being distance from the origin, a rho slice is going to be part of a sphere. Oh, geometrically a little bit harder to visualize, and that's kind of bad news. A little discouraging. There's some great news to follow, though. Again, with the tips and tricks, only one of these 6 possible orderings of these differentials is worth talking about. And again, in my, I don't even know, I'm scared to calculate how many spherical coordinate integrals I computed way back when in my undergraduate days. I never saw one naturally arise in a real application setting where an ordering other than this would have been helpful. It just basically doesn't happen, right? So I would encourage you to just always go with this ordering of the differentials. D rho d phi d theta, always that order. Okay. Now there are some situations where it doesn't matter. And that's not what I'm talking about. But there is no situation that I recall in which this is not just as good as anything else. Okay, so that said, now same follow-up tip. Always write down your stretching factor as you are writing down your differentials. Again, there is never any reason to talk about d rho d phi d theta by itself. Not geometrically natural in XYZ space. It's just not a thing, right? So should never. It doesn't make any mathematical sense or strategic sense to write down d rho d phi d theta alone. Makes no sense at all, right? So please, always, if only for the strategy of it, always write this whole thing down all at once. Rho squared sine phi d rho d phi d theta, all at once. And then that'll help prevent you from forgetting to write down the stretching factor and leaving all those points on the table, right? So make sure to get those points. Easy to do. Okay. All right, let's see an example here. And we're going to look at this ball. Centered at A on the z-axis, radius A. So it's like it's sitting on top of the xy plane at the origin. Okay, so let's go through our slicing process. What do we get when we take a theta slice like that? And geometric appeal, we get this half of a disk. Pretty easy pitch, I think. Right? That's what a theta slice looks like. Right? Okay. All right. Now, for what values of theta? Right. As theta increases, how far do I go until I am done? And I think it's again a pretty easy sell that this just goes all the way around 0 to 2 pi. In fact, I'm going to point out a nice sort of streamlining of this process. If your solid entirely surrounds any part of the z-axis, your theta bounds are going to be 0 to 2 pi, right? So you can see this, at least part of the z-axis here is embedded inside of that solid, and so 0 to 2 pi. Okay, does everybody buy that? Okay. Okay, cool. So there's a theta slice. Now we're going to fix a let me do it like this. We're going to fix this theta slice. We're going to focus all of our attention on that theta slice. But before I get to the next thing, I'm going to show you, this is just a kind of an artistic trick. This is just a preference. This is not mathematically necessary, but I find it very strategically helpful. And that is to redraw that theta slice. Here's the problem. The way I'm looking at that theta slice right now, I'm looking kind of from an angle. It's kind of distorted in the sense that, that right there I know is a right angle. In 3 space, that is a right angle, but it doesn't look like a right angle on the page. right? That's messed up, right? So if you just redraw the same theta slice, but as if you're looking straight on at it, right? Now, notice this angle that in space is actually a right angle. It looks like a right angle on the page. And it makes it just a little bit easier to understand what's going on and to do your, move on to the sort of the next phase. So again, that's not required. I think it's a useful little hack. Okay, so now let's think about our phi slices. A phi slice, as previously discussed, is going to be something like that, keeping in mind that phi is measured as that angle off of the z-axis, measured at the origin, of course. Right? So phi is that angle. Okay. Right. So first and last of these phi slices. Well, the first one is going to be up there, where phi is 0. Right, and the last one, as you proceed along, as the angle gets higher and higher, as phi increases, and I'm getting closer and closer to horizontal, you see these cross sections are getting shorter and shorter, and the very last one is going to be there, where phi is pi over 2. Is that cool? Everybody's happy? Okay. All right. Okay, so there's my phi bounds. So now, as usual, we're going to focus now on just a phi slice of our theta slice. And just to clean up the picture a little bit, let's redraw that there. And let's think about rho now. Our rho bounds. Rho starts at that point. What can I say about that point? Well, don't forget, that's just a redrawing of that point, which, don't forget, is just a redrawing of that point. That's the origin, right? So the point that defines my lower bound for rho is the origin, where, of course, rho is 0. Yeah? Okay. All right, upper bound, that point, a.k.a. that point, which, of course, is on this curve. Oh, wait a minute. What is that curve? Where did that curve come from? Oh, right. That curve, don't forget, it's just a redraw of that curve. So when I say that the point I care about is on that curve, of course, is part of the sphere. So that's really just saying that I need to understand the sphere. The point that defines my rho upper bound is on my sphere. Now, here's where the bad news kicks in. I'm going to have to write down the equation of that sphere. And when I say I mean you are going to have to write down the equation of that sphere. You have a description, the center, the radius. You can write down the rectangular equation. And then you can do all of that Chapter 1 conversion stuff and persuade yourself that that rectangular equation converts to this spherical equation. I just left a significant amount of trig for y'all to crank through on your own. Make sure you can do that, right? You can see how that's naturally going to arise in these kinds of situations. So this is the result. Our goal here, like what were we doing in the first place, is we were trying to find the upper bounds for rho. So in this equation, I'm going to solve for rho, and there's our upper bound for rho. Everybody buying it? Okay. Cool. Okay, so again, notice stretching factor right there, right? And so, make sure to put that in there. Again, really ought to do that before you write down the d rho d phi d theta, just to make sure that you don't forget. Okay. All right. So now you will have noticed by now that the picture comes up a lot. It's just unavoidably critical, I'm going to say, when you're doing triple integrals in spherical coordinates. You've got to have a picture. It's very difficult to make reasonable conclusions from teeny tiny little postage stamp sized little pictures. Please don't draw the itty bitties, right? Don't forget you have couple of pages of scratch at the back of the exams, for example, right? So you can practice draw all you want. Don't forget as well, you have the backs of the pages that the questions are written on as well, right? So you can draw a nice, big, luxuriously large picture on the back, and there's plenty of space, right? So don't try to save space with your picture. That's penny wise and pound foolish, as they say. Second point, don't expect that you're just going to, see it all in your mind and then just, boom, just draw a beautiful picture. That's really hard to do. That is, in many cases, I can't do that, right? Simple cases, yeah, sure. But in complex cases, you really need to go through a revise and improve process. So your first drawing, you should expect to be poor. But at least from that first drawing, it'll help you understand the actual shape a little bit better. And you'll be able to look at your first drawing and see what's bad about it, right? And then your second drawing will be better. Your second drawing will help you understand the nature of the shape better, thus allowing your third drawing to be even better than that, right? And so there's this whole process, and you can revise and redo as many times as is necessary. You've got all this scratch space, of course, on the exams. Keep redoing it until you feel like you have a good figure. And then, of course, you do have to put the good figure, your final draft, it does need to be in the space provided, right? But again, give yourself that advantage. It's way easier to make a good drawing if you give yourself several drafts. Somebody asked me one recently in office hours, I think it was Wednesday, and I did 6. My first one was not good. My second one was improved. My third one got a little bit better. I felt like I kept getting them better and better, and the sixth one was really good. So, give yourself that advantage. Lastly, this is not a matter of channeling whatever your natural inborn talent is. That's really not what this is. There are things to know. There are tricks. Right? So give yourself that advantage of, don't try to just go through the school of hard knocks and reinvent the wheel all for yourself. There are tips and tricks out there. Find them. Right? Everything that I know about mathematical figure drawing, which I like to think I'm pretty decent at it, I've put in those videos on the miscellaneous topics playlist, right, and my YouTube channel. Give them a look. Hope you find those useful. Everything that I know about it is in those videos. And there are carefully detailed explanations of complex figures that I work our way up to that you'll be able to see how that works. Yeah.
Are we able to have a ruler on?
I should send out a class-wide announcement about that. But so a straight edge, yes. One of those rulers that has a bunch of equations written on it, like they like to sell at Walmart, no. Right, so but just a plain old straight edge, totally fine, and in fact encouraged. Yeah, absolutely. Would you do me a favor? And if I don't send that email it's not going to be today. If I don't send such an email by the end of spring break, I would love a reminder. Thank you. Okay. Lastly, getting good at the techniques that you're going to learn is not just a matter of kind of watching it and I see what they did there, and then just doing it for yourself. It's not like that. This is chops. This is skill, and so you need to give yourself practice on that. So it's just like learning how to dribble a basketball, right? This being Duke, that's my metaphor. So you can't just kind of watch what the pros do and see what he did there, right? And then all of a sudden claim that you have that skill. You don't. You've got to spend time with the ball in the hand. And so give yourself the time as necessary to develop those skills with practice. Okay, speech over. Next example. A different ball, radius A, this time centered on the y-axis instead of the z-axis. All right, now this is a totally different geometric situation. Yes, it's still a ball. Yes, it still has the same radius, but it's on a different axis, and that really does change everything. One thing you're going to notice quickly, this ball here is entirely on this side of the XZ plane. Right? It just barely touches at that, just at the origin, at the only point on my solid that even so much as touches that plane. It does not go through to the other side. So this does not surround any chunk of the z-axis. So we should not expect theta to go from 0 to 2 pi on this. It doesn't encircle anything. Does that make sense? So, you got to think about what these cross sections look like, and with this observation in mind about the XZ plane, in some sense you might say the surface is tangent to the XZ plane. And so with that in mind, and thinking about these cross sections, these theta slices being disks that look kind of like that, geometric appeal, again, this is just purely geometric appeal. I say that our first theta slice is going to be like that in the x-axis direction, right? And then our last slice is going to be like that in exactly the opposite direction. And so theta is going to go from 0 to pi. Let's see, I can do it like this. Here we go. Yeah. Theta from 0 to pi. Now, like I say, geometric appeal there, right? That's just what the picture tells us. Can anybody see that geometrically? I know it's 3D visualizing is challenging. We just have to see that. Everybody good? Right. Okay. So all right. Now we're going to, as usual, pick a theta slice, and on this theta slice, rather than try to understand angles while viewing from a weird perspective that distorts angles, I'm going to redraw that theta slice over here like this, and think about this point of view on that theta slice. And with that point of view, let's think about phi. And phi slices, of course, are like so. And I can think about sort of the first few values of phi, and then as phi increases, it kind of goes along like that. And again, we have to think about first and last. And I claim, again, geometric appeal, that phi is going to start, I missed again, it's going to start at 0, right, straight up, is phi equals 0, and then it's going to end straight down, which is where phi equals pi. What do you think? Everybody buy that? And again, it's just a matter of seeing it from the picture. Okay. All right, and now with the phi and theta both fixed, in other words, looking only at my little phi slice of my theta slice, now let's look at rho. Rho starts at that point. Let's not forget, of course, that's really that point. So rho starts at the origin, namely where rho equals 0, and so we start rho at 0. Rho ends at that point, which is on that curve. Okay, well, yeah, but that's actually this curve. So when I say I have a point on that curve, I have a point on the sphere. And here we are again with a bunch of trig that's going to have to be done, because I can write down the rectangular equation of that sphere. Right, I know the center, I know the radius. Rectangular equation's easy. And then you got to go through all that chapter 1 business and convert that equation to spherical coordinates, which gives us that. Now again, make sure you can do that. All right, that's a chapter 1 flashback. Hopefully no surprise, right? We've talked in the past about how this class is very vertical. Everything later in the course kind of builds on stuff that was earlier in the course. So this kind of flashback happens a lot. Okay, so again, to get the upper bound for rho, we solve for rho, thus giving us that as our upper bound for rho. Good? All right. Okay, last example I'm going to show y'all. Now, this one, it does have some algebra involved, and I'm not going to spend any time talking about that. Really, the reason I like this example is because of the really clever artistic trick that I'm going to use in relation to this. So first of all, let's talk about the set itself. You can see we're looking at what is inside of a certain sphere, but also outside of the other sphere, and altogether our domain here is this weird shape that I'm going to kind of draw like that, but this isn't really actually what it looks like. If you think about it, if you have a solid ball, and I like to imagine a big round scoop of ice cream, all right, such as you get from those certain ice cream scoops, that make the spherical sort of. So anyway, you take a big round scoop of ice cream, and now take one of those scoopers and scoop out a spherical chunk out of the bottom of it. There's actually ice cream, right? There's kind of a lip, kind of an edge, if you will, kind of a rim around the bottom there as well. But the problem is, if I draw it like this, well, then it looks like it's kind of solid in here, but it's kind of hollow in there. I mean, there's ice cream on the near edge and the far edge, but it's hollow in the middle. It's just a hard thing to draw, right? So, okay, if I have this hard thing to draw, and if I need to talk about taking cross sections of it, right? Do I have this challenging sort of, I don't know, something maybe kind of like that. If I need to take that what I'm calling this intersection, if I need to take a cross section of that intersection, that's geometrically confusing, I think. And again, maybe you're better at visualizing things 3D, and I hope, and that's cool. But anyway, a lot of us are going to find that pretty confusing, right? So here's the wonderful trick. If you want to take a cross section of an intersection, you can instead look at the intersection of the individual cross sections. Now let's talk about the individual cross sections. Forget about the actual solid. If I think about this entire ball, right? And if I look at a cross section of that individual cross section is easy. That's just a ball. I'm taking a slice with a half plane. That's going to give me half a disk. There's nothing to it. That is just this. Right? And then likewise, this green chunk that I'm going to take out of my orange, what's the cross section of that green ball? Well, it's a green half disk. Nothing to it. It's just this. Right? So I don't have to try to visualize this very confusing solid that's, again, the part of the orange that's the outside of the green. I can't draw it, that's hard to visualize. And thinking about slicing up that confusing thing, I can instead just look at, okay, well, here are the individual cross sections. And what's the part of the orange that's outside of the green? Well, nothing to it. It's just this. It's just that blue thing right there. A lot easier, right? And again, so the goal of this discussion was just to present this artistic trick that you can look at the individual cross sections and then intersect them after the fact. And artistically, much easier. Now, lots of little details remain as to, how do you interpret from that solid, how do you interpret these bounds? So you want to think that through, go through the usual process, phi slices, rho slices. There's details here that you can sort of work your way through. I will point out that there is this handy-dandy little equilateral triangle right there that helps us understand my upper bound for phi, right? So that's convenient, right? But algebra remains. Make sure you can fill in those blanks. Is that cool? Everybody happy? Okay, so I want to move on to the last third, if you will, of section 5.5, and I'm going to confess this is not covered so much in 5.5, but I think this is really important. I think it's a really tragic, I don't want to say omission, but I think it's undersold in this book, and frankly, it's undersold in most multivariable calculus textbooks, and that's the idea of symmetry theorems. In my undergraduate days, I computed so many integrals, and a great fraction of them I computed by this method. I think this is one of the biggest techniques for computing double and triple integrals, is the symmetry theorem. So we're going to segue into this real quick by flashing back to single variable calculus. You may recall this theorem down here that says that if you have an integrand that is odd, don't forget this is what odd means, and if you have a domain that is symmetric, and there's different ways to think about what symmetric means. I like this idea about you can relate symmetry to reflection, but in practice you probably recognize from your single variable calculus class a symmetric interval as being from negative a to a, where the lower bound and the upper bound are negatives of each other. Right? Again, I find it more natural to think of this as an interval that is its own reflection. When you take this interval and reflect it over the origin, same thing. Right? Okay, so when that happens, when you have an integral, the integrand is odd, the domain is symmetric, your integral is 0. Walk away. Done. No anti-differentiating, no substitutions, no integration by parts, no partial fractions, none of that funny business. Right? No problems at all. Just boop, 0. Done. That's a pretty cool theorem. Now, I know that in single variable calculus it doesn't really come up that much, but in multivariable calculus this actually comes up quite a bit. So what we're going to do is generalize this to a multivariable setting, and in order to do so, the first thing I want to do is just make sure we understand why this is true. And the big idea is here's your symmetric domain, and if the function is odd, then this term, if you will, in the Riemann sum, and this term, if you will, in the Riemann sum, are negatives of each other, and if they're negatives of each other, then they cancel, and of course every one of those green terms pairs up by the symmetry with a corresponding orange term, so everything cancels. Right? It's a nice way to think about why this theorem is true. Here's a different point of view concerning substitutions. This is a pretty cool trick. You may have seen this before, but this substitution where x is minus u is the trick that ultimately makes it work. Just plugging in x equals minus u. Now notice I'm capitalizing on the fact that the domain is its own reflection. And I'm also capitalizing on the fact that the integrand is odd. So you can see the oddness right here. You can see the symmetry right there. And the nice little punchline is that, putting this all together, we have just shown that this integral is its own negative. And what number could possibly be its own negative? Well, only 0. And so this integral has to be 0. So real clever little proof. And notice again that change of variables, well, substitution, but that's just single variable change of variables, is the trick that makes that work. Okay, so let's see. We are next time going to talk about how to generalize that to 2 dimensions, and that's where we're going to start getting real big payoffs. Y'all have a great spring break. See you in 10 days.